In this video, we'll continue off from the last video, so make sure you have seen that, by looking at the simple kinetic molecular model. Particularly, we're going to focus on these three syllabus points. At the end of last video, we introduced this equation. Pressure times volume, PV, is equal to a constant. And this is only when the temperature is held constant. So let's look at what that means now in more detail, particularly with one past paper question. So, what does this equation mean? Well, let's start over here on the left-hand side. This equation, PV equals constant, PV equals constant, can also be written, and perhaps a better way to learn it, P1V1 equals P2V2. What does the 1 refer to? Well, the 1 just refers to the initial conditions. This will always involve some sort of change. So it might be the pressure is 10 and the volume is 5 to start with. After the pressure is changed to 20, what happens to the volume? So the 2 refers to the final condition, so how it ends. So you can use it in either form. You could use this equation and find the constant, and remember that would be equal to the pressure and the volume at the end. This is at the start. Or you can just remember it as P1V1 equals P2V2. And this is known as Boyle's law, named after the Scottish scientist, not Susan Boyle. So let's use that equation now in this nice little question over here. I'll give you a chance to read that, or pause the video now actually so you can have a read of that. Okay, so let's look at the key points. It's held at ground level, and the volume, so that's something we're probably going to have to use, is 4,800 meters cubed. The pressure of the gas inside it is 98 kilopascals. The balloon is then released and rises to a height where the volume is 7,200. So you can see how we've gone from the initial, the initial conditions, so P1 and V1, to the final, or to P2, V2 conditions. We're asked to find the new pressure, so we're basically trying to find P2. And the first thing to always do with these questions is think about what you want to find. Note the temperature stays constant, because remember, this equation only works when temperature stays constant. First thing to always do in an exam for any mathematical question is write the equation, because there's normally a mark for that. And this is one of the equations you need to remember. I'm going to use it in this form as shown here. So the pressure initially, I look at my question, the pressure is here, and it tells me it's 98 kilopascals. Now, you can deal with the kilo, so that would be 1,000, put that in there, or you can just do it without the 3 zeros, and just remember that your answer will be in kilopascals. I'm going to do it that way, it's a bit more pleasing on the eyes. V1 is over here, so that's the initial volume, and that's 4,800 meters cubed. This is equal to the pressure 2 in the second, so at the end, pressure at the end, P2, and that's what we want to find, times by the new volume, which is 7,200 meters cubed. Quick check, these two units need to be the same because they're going to cancel in a minute. The next thing I do, 98 times 4,800 in my calculator, and that gives me funky pen, let's go back to black, 4,70400 equals P2 times 7,200. Now I need to rearrange this equation. I need to get P2 by itself. Well, the way you do that is remove the times 7,200 by dividing both sides by that. And that gives me an answer of 65. So if I divide this number here by 7,200, I get 65.3. Given all the numbers in the question are given to 2 sig figs, I'm going to give my answer to 2 sig figs, but we need units. Don't forget the units. Well, I look back, see what units the pressure was in there, and this is just the same, so it's kilopascals. It's just why it may be necessary to release helium from the balloon as it rises ever higher. Well, as it rises higher, hopefully you're spotting that the volume of the balloon is increasing. Now, it could keep increasing, but eventually, it's a balloon, the gas can't go anywhere, so the balloon's probably going to pop. or burst. And that's what they're looking for here. By releasing the air, the helium out, that will reduce the pressure and stop it bursting. But all you need to write is the idea that the balloon will burst. Let's have a look at another question related to this. A bubble of gas from the mud of the bottom of the lake rises to the surface. Now, look, read the question carefully. There's a clue. You need to put one tick in each row. So don't do more than one tick, otherwise you're going to be wrong. And we're assuming that no gas or water vapour enters or leaves the balloon. So the number of molecules in the balloon stays stays constant. Here's my mud. The balloon's released, and perhaps if you've been scuba diving or swimming underwater and released bubbles, you notice that as the the bubble rises to the surface, up here, this is water here, the bubble gets bigger. Well, why is that? Well, you remember that the pressure in a liquid is equal to rho GH, so the pressure is greatest down here. When the pressure is greatest, that keeps the bubble the smallest. But as the pressure reduces, the volume is going to increase. Whoops, excuse me. The volume is going to increase there. What about the mass? Well, as we said, no water vapour enters or leaves the bubble, so the mass of the bubble is going to stay the same. The reason being that no extra atoms are getting in or leaving, so the mass can't change. That's just the total number of atoms there. Now the density, well, I'm thinking, well, what's the equation for density? Density is mass over volume. If the mass has stayed the same, so stayed constant, but the volume has increased, then we're dividing the same number by a bigger number, so we're going to get a smaller density. So the density is going to decrease. So that's this syllabus point dealt with. Let's now have a look at evaporation. Now remember, we're going to explain evaporation using our simple kinetic molecular model, which is the whole point of this section. Let's have a look at this animation here, which shows a gas, probably going towards a liquid, vibrating in the middle. And what I can do is I can increase the heat on this. And what you'll notice is that as I increase the heat, eventually some molecules, the ones that are moving the fastest, fly off. There's a couple free going up there towards the top, a couple there. And this is evaporation. It's not when the whole gas is bubbling off. It happens over a range of temperatures. And it's where the molecules moving the fastest have just the right amount of energy, or just enough energy, I should say, to escape the surface. And evaporation only happens at the surface, and become a gas. So let's have a look at evaporation and what you need to know about that. So here's our container, here's our liquid, and remember, we're considering the molecules as little spherical balls, I suppose, moving around randomly and quickly. As we heat this up, and we don't even need to heat it up, it happens at a range of temperatures. It might be happening evaporation. Well, yeah, I'll tell you what, think about on a cold day, you see a puddle outside the classroom. If you come back a bit later on, the puddle hasn't got over 100 degrees, otherwise you'd feel that on your foot. It hasn't boiled, but the puddle's reduced in volume, and that's because of evaporation. And it's because just sometimes some molecules might just have enough energy to escape the surface, the great escape. And the great news for them is they are now a gas and they're free to move. They've escaped the surface and they're free. And that's when they've got just enough energy. Also, if I warm this up, then more molecules are going to have enough energy. So more will escape. Evaporation happens quicker. And we'll talk about that in a moment. But just remember, evaporation is all about molecules escaping the surface. It doesn't happen at a set temperature like boiling. So boiling for water happens at 100 degrees Celsius at sea level. And evaporation, however, happens anywhere really between 0 and 100 degrees Celsius. So anywhere in that range, we get evaporation. If you look back at your syllabus, we've talked about the fact that evaporation involves the most energetic molecules escaping. Now we need to relate it to temperature, surface area, and any sort of wind or draft, as they've put there, over the surface, how it influences evaporation. Let's start with let's start with what happens with temperature. So as the temperature increases, so we make it warmer, well, more molecules are going to have enough energy, and then we talked about this a moment ago. More molecules are going to have enough energy, and enough energy to escape the surface. So the rate of evaporation is going to increase. So as the temperature increases, the rate of evaporation increases, and that's because more molecules have enough speed to escape the surface. Let's now think about in terms of surface area. So let's compare these two vessels here with some water in them. Well, on this one, there is a much larger surface area, here it is, for the molecules to escape from. So that's going to increase, so larger surface area, the evaporation is going to increase. Because here you can think they can only escape from here. It's a much smaller area for them to escape from compared to this one. The final one refers to any sort of wind over the surface of that liquid. Well, let's consider these molecules, these water molecules, evaporating. So some near the surface have escaped. Now when they escape, they tend to hang around quite close to the water. Some will go flying off, but some will be near the water. Remember, there's billions and billions of molecules, so some will stay there. Now, if they're there, they're kind of blocking further ones from evaporating. So if there's no wind, but still, the rate of evaporation is not as high, so we'll say lower, compared to when there's a wind. Well, why? If there's a wind, the wind's going to come along, here it is, the wind, and it's going to remove any molecules already near the surface, clearing the way, there they go, goodbye molecules, clearing the way for more to evaporate. So when there's a wind across the surface, wind equals more evaporation. And you might notice that puddles disappear quicker on a windier day. They also disappear quicker in, say, somewhere like Christchurch, which is less humid, than in Auckland, because humidity is related to how many water molecules there are in the air. The final thing with evaporation is to consider what happens to the leftover ones, the ones that don't make that great escape and become a gas. Well, as we said, the ones which escape are the ones with the most energy, are the ones that escape. Well, what happens to the ones that are left behind? Well, these are the ones with the least energy. They're already a bit lethargic. There it is, a bit sad, a bit lethargic, least energy. So the ones left behind are the low energy ones, or lower energy, I should say, compared to the ones that escape. So the average energy, of remaining particles is lower. Because the average energy of the remaining particles is lower, well, the temperature is going to go down. So the temperature of this water here, the one left behind, reduces because the highest energy ones, remember those are the warmest ones. Remember the temperature is related to how fast the molecules, or how much energy So, just to recap, the temperature is related to how much energy the particles have. In evaporation, the most energetic ones are the ones that escape. Therefore, the average energy of the remaining particles is lower, is reduced, and that is because the faster ones are escaping. Given that energy is related to temperature, as we said down here, well, if the average energy is reduced, then the temperature of the remaining liquid is going to go down. So when things evaporate, the actual temperature of the water left behind reduces. So just to review, we've now covered this, demonstrating understanding, so we need to explain it in terms of the molecular model, why temperature, surface area and draft affect the rate of evaporation. And then finally, the last one, which we just talked about, is how the rate of evaporation, how evaporation causes the liquid remaining to cool down because the highest energy particles escape.